Your server is down. The fix is one command. You just can't remember which one. That's the gap this video closes. Every command a Linux sysadmin actually types, all 109, each one running on screen. Welcome to the NBX Studio. Here's how we'll keep 109 of anything straight. Your terminal is a workbench, every command is a tool, and the tools live in 10 drawers. One warning first. Somewhere in these 109 sits a command that wipes an entire disk in 4 characters. No prompt, nothing in a bin. So, which one is it? We'll get there. We'll work through the drawers in order. Files, and the text inside them. Then who's allowed to touch what. Then the processes running right now and how you watch a machine properly. Then disks and the network. And finally the jobs and sessions that outlive you closing the laptop. Drawer 1. Moving around and handling files. Your project lives a few folders deep and you want to work inside it. The command is cd, short for change directory. One way in is an absolute path which begins at the root / and the shell walks down at a level at a time. The root of the disk into home, where every user's folder lives, into Santhu, your own account, and finally into API. The other way is a relative path, which begins wherever you're standing. To reach the logs folder beside you, type cd /logs, where 2 dots mean up one level, and you drop into logs. None of those folders moved. Only where you're standing changed. So a path is just directions to a place which was already there, and cd walks them for you. Here's something which happens more often than people admit. You've been jumping between folders, and you genuinely can't remember which one you're sitting in. The command which answers is pwd, which stands for print working directory. Pwd replies with the whole path, read top down. The root of the disk, then home, which holds every user's folder, then Santhu, your own account, and finally API, where you're standing. Joined up, that's the full path. And it's the same answer no matter where you started from, because pwd will never hand you a relative path, and never a shortcut either. Pwd answers from the root every single time. When a script needs to know where it is, pwd is the answer it can rely on. You want to see what's inside a folder. ls, short for list, gives you the names and nothing else, which is fine until you need detail. Add the -l flag for long, and you get ls-l, where every file becomes a full row. That row carries the permissions, saying who may read, write, and run it, the owner, the account it belongs to, the size in bytes, and the date it last changed. Those raw byte counts are hard to read, so add an H for human and you get ls-lh, which turns 4096 into a plain 4 kilobytes. Same directory each time. You're just asking for more of the truth. Reach for ls-lh by default, because the extra columns cost you nothing. You need a new folder, so you reach for make-dir, short for make directory. Inside projects, which already exists, it drops API into place without fuss. Now try asking for a path 3 levels deep in a single command, and it refuses outright. Make-dir only ever creates the last folder in a path, and here the middle level doesn't exist, so make-dir has nowhere to put the bottom one. The fix is the -p flag, short for parents, so you type make-dir-p and make-dir builds every level that's missing. src appears inside API, and then handlers appears inside src. Without -p, the parent has to exist first. Type -p out of habit, and you'll never meet that error again. Touch looks like a command which does nothing at all, which is exactly why people skip straight past it. Start with a name that doesn't exist yet. Run touch on it, and Linux creates an empty file for you, 0 bytes, no contents whatsoever. So far, so unremarkable. Now run touch on that same file a second time. The contents don't change because there are none, but 2 clocks attached to that file do move. The modify time, which records when the contents last changed, and the access time, which records when it was last read. And build tools watch those clocks. The content itself is never touched. Touch exists to move a clock forward, and which turns out to be worth a whole command. CP, which is short for copy, makes a genuine second copy of a file. So the original stays exactly where it was, and a second file comes into existence holding its own bytes. If what you want is a whole folder and everything inside it, add the -r flag, short for recursive, and cp-r walks the directory so that every file underneath is copied as well. Here's the part which matters. You now have 2 independent files that merely happen to hold the same contents. Edit the original and the copy doesn't follow, because nothing connects them. That seems obvious until the afternoon you edit the backup by mistake. Copy when you want two things. Move when you want one thing somewhere else. MV is short for move, and it's also how you rename things, because renaming really is just moving a file to a new name in the same folder. The trick is to watch the file rather than the name on it. You start with notes.md, and underneath, the disk knows it by a number called an inode. Rename it and you get a new name sitting on the very same inode. Now move it into another folder and the path changes while that inode stays exactly as it was. No second copy was created, and not one byte was rewritten. The one exception is moving between two disks, and then the bytes really do travel. Inside one file system, nothing is copied. That's also why moving a file to another disk takes time, when renaming it never does. RM is short for remove, and the first thing to understand is that Linux has no recycle bin waiting to catch a mistake. Point plain RM out of folder and RM refuses, because on its own it only deletes files. Add -i for interactive, and RM-i asks you to confirm every single file before it goes, which is slow but survivable. The combination people actually type, though, is -rf, meaning recursive and force. Run rm-rf and it recurses into every folder underneath while force suppresses every question it'd have asked. 412 files gone, without one confirmation. There's no undo here, and no command that brings them back. Type the path out in full before you press return every single time. LN, short for link, gives one file a second name. To see why which matters, look at the data itself, sitting in one place on the disk. A plain LN creates a hard link, a second name pointing straight at that data, and the link count, which counts the names attached, goes up to 2. Now add -s for symbolic, and L and -s makes something quite different. A link which points at the name rather than at the data. The difference stays invisible until you delete the original name. The hard link carries on working perfectly because the data was never tied to that first name. The symbolic one is now pointing at nothing. The data survives until the last name goes. Use a hard link for a second real name and a symlink when you want a pointer. Your terminal has turned into an unreadable mess, so you run clear. The screen was full of output, and above it sat the scroll back, everything that had already scrolled off the top. After clear, the screen looks empty, which is genuinely useful. But look at the scroll back, because it's entirely intact. Scroll up, and every line you thought you removed is still there. If you want it properly gone, reset is the heavier tool, and after reset the scroll back goes as well. Clear is cosmetic and reset is not, which matters on a machine somebody else can scroll back through. On somebody else's machine, assume clear removed nothing at all. Quick check. You delete the original file. Which link still works? Have a think and pause here if you want longer. Ready? The hard link, because it points at the data. Drawer 1 is your hands. Move with CD, look with LS, build with make dir and touch. Duplicate with CP, rename with MV, delete with RM because there's no undo. Drawer 2. Reading text and finding it because most of the job is reading. Cat is short for concatenate, and its actual job is to print a file straight to your screen. Point it at a small config file 3 lines long, and you get the whole thing at once, which is exactly right. Now take a log file with 10,000 lines in it and run cat on that instead. Cat does exactly the same thing because printing everything is the only behavior it has. The output scrolls past far faster than you can read. There's no way to pause it and no way to scroll back to the top. Cat has no breaks, and that's precisely what less was written for. Use cat for a config file you can see all of, and less for anything bigger. Cat prints a file from the top down, so you get line 1, then line 2, then line 3, oldest first. That's the wrong way round for a log, where the line you care about is nearly always the last one written. Somebody noticed and named the fix by spelling cat backwards. That tool is tac, and tac reads the file from the bottom upwards. So the crash at 9:47 arrives first, and the startup message from 9 o'clock comes last. And the file itself is untouched, only the output order changed.
No flags, no pip, no arguments.
In most logs, the line you want is the final one. Tac is a one-word change from cat, and on a log it saves you a scroll every time. Before less existed, this was the tool everybody used, and it's still on every machine you'll ever log into. You point more at a file far longer than your screen, and more hands you the first 40 lines or so. Press the spacebar, and it moves you down to the next 40. That much is genuinely useful. But now try to go back to something you just read, and you simply cannot because more only ever travels forwards. Not even one line back. And once you reach the bottom, it quits on you. And which is why Les replaced it. One direction, then it exits, which is the frustration Les was built to fix. You'll still meet more on a stripped-down system, so it's worth knowing why it annoys you. Les does everything More did, and then fixes what More got wrong. You can scroll down a page at a time, and crucially you can scroll back up, which More could never manage. Then there's the part which genuinely surprises people. Open a 10 GB log with Les, and it appears on screen instantly because it never loads the whole file into memory. It reads only the piece you're looking at. And when you know roughly what you're hunting for, press / to search inside the file, and it'll jump straight to the match.
Which is why file size stops mattering.
Les is the reader you should reach for by default, whatever the size of the file. In a log of thousands of lines, the ones you want sit at the bottom. Tail gives you exactly that. The last 20 lines, nothing above them. That alone saves a lot of scrolling, and most of the time it's all you need. But the flag which genuinely matters here is -f, for follow. Run tail -f, and the file is held open, so new lines appear as the service writes them. A request comes in live. Then another. And then the upstream timeout you were waiting for. Tail never exits on its own. Control-C is how you let it go. Tail is the command you leave running while you reproduce the bug. 2 windows. Tail -f in one of them, and the bug tells you about itself. VI traps more beginners than any other command on this list, and the reason is modes. When it opens, you're in command mode, which means the keys are instructions rather than letters. Press J, and you move down. You don't type AJ, which is why typing your name appears to do nothing sensible. Press I, which stands for insert, and those very same keys now produce text on the page. When you're done, press escape, and they turn straight back into commands. To save and leave, type a colon, then W to write the file, then Q to quit the editor. Escape, colon, W, Q. Memorize that one sequence and VI stops being frightening. And if you ever land in 6 by accident, that same sequence is how you get out. You've 2 config files which are almost identical, and something in one of them has broken the service. Rather than read both and trust your eyes, run diff, which walks both files line by line at the same moment. Everything that matches is dimmed away, and nothing else is mentioned at all. What's left is the pair which genuinely differs. The old listen line on port 80, marked as removed, and the new one on 443, marked as added. 2 entire files reduced to 2 lines. Add -u for the unified format. That's what every patch you've ever applied is written in. Before you edit any config on a live server, diff it against the one that worked. Find does exactly what the name says, and find does it the hard way. Find walks the entire tree beneath wherever you point it, folder by folder, testing every file against your conditions. Ask it for anything ending in .log and API.log matches, while notes.md is rejected because it's not a log. Condition stack, so add -m time -2, and you're now also asking for files changed in the last 2 days. Web.log is 2 hours old and stays, but old.log is 90 days old and drops out. There's no index behind this. Find is slow because find genuinely looks. When correctness matters more than speed, find is the tool which will not lie to you. Locate answers the same question as find, but in a fraction of a second, and the reason is worth knowing. Somewhere on your machine sits a database of file names, rebuilt in the small hours. Locate never touches your disk at all. It only searches that database. So a file you made last week is in the index and comes back instantly, with no walking at all. But ask it for a file you created at 8 this morning and you get nothing because the index hasn't been rebuilt since 3. Running updated rebuilds it on demand. Locate can be fast and wrong at the same time, so use find when it has to be current. Reach for locate when you're guessing, and find when you need to be certain. grep searches inside files and prints every line containing what you asked for, which makes it the single most used tool on this list. The name comes from an old editor command, global regular expression print. A few flags carry most of the weight. -I ignores case, so timeout and timeout both match. -r searches whole directories rather than one file. -c, for count, gives you just the number of matching lines instead of the lines themselves. And -v, for invert, returns everything that doesn't match. That last one hides the noise. -v is the flag people forget they have. grep is the tool you'll type more than any other, so the flags repay learning properly. Awk is named after the 3 people who wrote it, and awk exists to pull columns out of text. Take one line of output. Awk splits it on whitespace automatically, without you writing a single line of parsing code, and numbers the pieces. $1 is the file system, $2 is the total size, $3 is the amount used. So asking for $3 pulls that column out of every row at once. And because awk runs your snippet on each line in turn, you can keep a running total and add the column up as it goes past. Which is why awk beats writing a parser for a one-off question. Anytime you catch yourself about to write a script to read columns, try awk first. Sed is short for stream editor, and sed edits text as that text flows past it. A line goes in, the pattern you gave it matches somewhere inside, and the altered line comes out the other side. There's a catch that bites everybody once. By default, it changes only the first match on each line. Add a G on the end for global, and it changes every one. And here's the bigger catch. Everything you've just watched printed to the screen, but the file on disk was never modified at all. Add -i for in place, and now it genuinely is edited. Without -i, sed only ever prints. Run it without -i once, read the output, then run it again with -i. Here's a pipeline which looks completely reasonable and quietly does nothing at all. Find prints its file names down the pipe, exactly as you'd expect. But rm doesn't read from a pipe. Zargs reads arguments, the words you type after the command. So the names arrive, nothing is listening, and not a single file is deleted, with no error to tell you. Zargs is the adapter that fixes it. Zargs sits in the middle, reads the incoming names, and hands them to rm as arguments instead, so the delete finally runs. If your file names contain spaces, use -print0 with -0. Whenever a pipe seems to do nothing at all, Zargs is usually the missing piece.
Quick one.
You want every line which does not contain the word error. Which grep flag? Have a think and pause here if you need longer. Ready? -v, because -v inverts the match. Drawer 2 is your eyes. Cat and less read. Tail follows. Find walks the disk, locate guesses. Grep, awk and sed search and rewrite. Zargs joins them, which is why pipes work. Drawer 3. Who you are and what you're allowed to touch. Change mod, spelled CHMOD, is short for change mode, and a file's mode is really just 9 switches. They come in 3 banks of 3. The first bank is the owner, the account the file belongs to. The second is the group, meaning everybody in the files group. The third is other, which is literally everyone else. Each bank has read worth 4, write worth 2, and execute worth 1. So 7 is 4 plus 2 plus 1. All 3 switches on, while 5 is 4 plus 1, read and execute with the write left off. If numbers don't suit you, the letter form sets exactly the same 9 switches. 7 is all 3. 5 drops the write. Read any permission string in 3s, and the number stops being something you memorize. Change own, spelled CHOWN, is short for change owner, and change own hands a file to somebody else. This file belonged to Santhu, and after running that one short command it belongs to the deploy account instead. Files carry a group as well as an owner, and very often you want to set the 2 of them together in one go. So add a colon and a second name, and you set both at once, making the group www. Now look carefully at what didn't happen. The 9 permission switches haven't moved a millimeter. Read, write, and execute are set exactly as they were before. What changed is that the first bank now describes a different person. Permissions describe a role rather than a person, which is precisely why these are 2 separate commands. So when a service can't read its own config, check the owner before you change the mode. Change the mode when the rules are wrong. Change the owner when the person is. Here's a question almost nobody asks. When you make a new file, where do its permissions actually come from? The answer is umask, short for user file creation mask. Every new file starts life at 666, read and write for everyone. Your mask, typically 022, lists the bits you never want handed out, and those switches are simply subtracted. What survives is 644, which is exactly what you get when you create a fresh file. Directories are slightly different. They start at 777 because you need execute permission to enter one at all, so the same mask leaves them at 755. And note that a mask never adds a single bit. It can only remove them, which is exactly what the word mask means. Umask can only take away. You'll rarely change your mask, but knowing it exists explains every new file you make. Run a mask once on a machine you administer, and every new file afterwards makes sense. Restarting a service is something only an administrator may do, so run it as yourself and you get permission denied, which is the system working as intended. The obvious fix is to log in as root, and it's the wrong one, because then every command carries full power and nothing records who you were. What you want is to borrow that power once. So put sudo in front, short for superuser do. First, a rule file called sudo is consulted to answer one question. Is this user allowed to run this particular command? If the answer is yes, the command runs with full root privilege and a line goes into the audit log naming you. And then the privilege is handed straight back, so the next thing you type runs as you again. Sudo lasted exactly one command, and that's the entire point. Use sudo for the command that needs it. Staying yourself is the safer default. User add looks like one small command, and it's quietly doing 4 things at once. User add writes a line into etc password, which is the account itself. User add writes an entry into etc shadow, where the password hash will eventually live. User add creates a group with the same name as the user. And then it stops, because the home directory isn't created unless you ask. That's what -m is for, short for make home, and with it the folder finally appears. While you're there, -s sets which shell they get. One short command, for separate changes. Forget -m, and that user logs straight into the root of the disk, owning nothing. Use user add -m-s, or use adduser, which asks you the questions instead. This user currently belongs to 3 groups, and you want to add a 4th. The command is usermod, and the flag combination is -a. The A stands for append, meaning add to what's already there, so Docker is added, and the other 3 stay exactly where they were. Now watch what happens if you forget that G on its own doesn't mean add. Usermod means replace the entire list with what follows, so sudo, www, and dev are simply gone. And since sudo was one of them, that user is now locked out of administering the machine. And no warning is printed. The command reports success. One missing letter, and you've removed your own access. Read that flag out loud before you press return. -G, append. Userdel removes an account, and userdel does exactly what you asked and nothing more. The account line disappears from etc password, so that person can no longer log in. But look at the disk. Their home directory is still sitting there, every file intact. And because the name that owned it no longer exists, the owner is now displayed as a bare number. The name is gone, but the numeric user ID it was attached to is still stamped on every one of those files. Add -r, and the home directory goes with the account. Which is why old servers are littered with folders owned by a number nobody recognizes, and worse, a new account can be handed that same number later. If you're removing somebody properly, remove their files deliberately rather than leaving them behind. Everybody has typed this command at some point in their life, and almost nobody stops to think about where that password actually ends up. The command everyone knows is passwd, and what it does next is the interesting part. What you type goes in one end. Passwd passes through a one-way hash, maths that's easy forwards and effectively impossible backwards. The result is what gets written to the shadow file. What you typed is never stored anywhere. There's no route back along that arrow by design. So when you log in later, the system hashes your attempt and compares the 2 results, never the passwords themselves. So even a stolen shadow file gives up nobody's password, and that's the entire design. Nobody can give your password back, not even the administrator, which is why a reset is the only way in. So when somebody asks you to look up their password, the honest answer is that you can't. Setting one password is fine. Setting 100 of them by hand on the morning a new team arrives and every account needs one is not. Which is why passwd exists. You give it a file of pairs, each line a username and the password it should get, fed down a pipe one line at a time. passwd works through them. Deploy is set, CI is set, and 98 more follow in one pass. Now, you couldn't do this with passwd, because passwd deliberately insists on being run at a real terminal so that a password is never sitting in a script or a shell history. A password should never sit in a script or a history file, and that restriction is deliberate. passwd is the one built to be automated instead. Use password for a person at a keyboard and chpacid for a machine doing it in bulk. Somebody else is on the server, and you'd like to know who they're and what they're up to before you restart anything. The command which answers is W, which is the shortest on this whole list and covers both at once. Santhu is on PTS0 in an editor. Deploy is on PTS1, running a sync. And here's Santhu again on PTS2 because they opened a second connection. That's 2 rows for one person, which trips people up constantly. These are sessions, not accounts. The header line across the top carries the load average, so you get a sense of the machine at the same time. W shows what each session is running and how long it has been idle. Who gives names and stops. W goes further. These are sessions, not accounts. Run W before you reboot anything because somebody else may be halfway through something. 2 rows for one person is normal, so read the TTY column before you assume anything. W tells you who's on the machine at this moment. The more useful question, once something has already gone wrong, is who was here earlier today, and last answers exactly that, going back weeks. Root signed in at 12 minutes past 3 in the morning, and whether or not that's fine, it's the row you stop on. Santhu logged in on Monday morning, which looks completely ordinary. The machine rebooted on Sunday evening. All of this comes from a log file called WTMP, which is worth knowing for one uncomfortable reason. A file can be edited by anyone who is root. So it's evidence rather than proof, and you check it early, before anything else gets touched. Last, the first place to look after a breach, and the first thing a competent attacker clears. Read last early, save the output somewhere else, and then start investigating. Sometimes you need a process to believe that one folder is the entire file system. The usual reason is repair. You've booted from a USB stick and want to run commands as though you were inside the broken install. chroot, short for change root, takes a directory and declares it the root for one process. From inside, everything above that directory simply stops existing. Run ls on / and you see only the jail. Try to climb out with ... and you cannot because there's nothing above you to climb into. But a root user inside can break out with the right system calls because it was never built to contain a hostile process. Containers do that job properly, using kernel namespaces. Rescue work is what chroot is genuinely for. Treat it as isolation, never as security. Keep crt for rescue work and let containers do the job it was never built for. Reach for crt when repairing a system and a container when isolating one. Quick 1. You change mod 64 for a script, then run it. What happens? Have a think and pause here if you need longer. Ready? It refuses. The execute bit is gone. Drawer 3 is the lock. Change mod and change own set access. You mask shapes new files. Sudo lends power and logs it. The user tools manage the accounts behind it. Drawer 4. What's running and how you stop it without losing work. PS is short for process status, and PS hands you a snapshot of everything running at this exact instant. Not a live view, a still photograph. Each row is a process, so here's PID 4821, which is node running your application, PID 1140, which is Nginx, and right at the top PID 1, systemd, the ancestor of every other process on the box. Of everything in that output, the PID column is the one to find. PS-EF prints the same data in a different syntax because 2 flavors of Unix disagreed about flags 40 years ago and both won. Every other tool on this list will ask you for that number. Get comfortable finding a PID quickly because almost everything after this needs one. PS gives you a flat list, which hides the most useful fact about processes. Every one of them was started by another one. PS tree draws that instead. At the top sits systemd, process number 1, which the kernel started before anything else. Nginx was started by systemd. A worker was started by Nginx. Those connecting lines are real relationships, not decoration. Now kill a parent in the middle and the line to it snaps, but its children aren't killed along with it. Instead, process 1 adopts them, immediately and automatically. Nothing is ever left without a parent, which is exactly how a job can outlive the shell that launched it. Whenever a process seems to have no parent, STRI shows you it was adopted rather than orphaned. PS shows you an instant. The question you usually have is what's happening now and which needs something that moves, which is top. Top shows the same processes, but it refreshes every couple of seconds instead of printing once. So node is climbing hard, Postgres is steady and clearly not your problem, and Nginx is almost idle. And crucially, the rows resort as it goes, so whatever is busiest keeps rising to the top on its own. You don't read this output so much as watch it. Press Q to leave. Top's the first thing to open on a slow box, because top shows you the shape of a problem rather than a single number. Watch top for 10 seconds before you conclude anything, because one frame tells you very little. Top works, but it makes you do arithmetic in your head. It'll not let you touch the mouse, and killing something means typing a number by hand. Top is that tool with the edges filed off. Across the top you get 1 bar per processor core, so a load of 4 on 8 cores looks like what it is. The colors in those bars separate kernel work from your own. Below, the process list is the same, except you can click a row with the mouse and press F9 to kill it, no PID required. And you can scroll sideways for the full command line, or press F5 for the tree view. Same numbers, far less squinting, and worth installing on every machine you look after. Install top on any machine you'll spend real time on. You'll stop opening top entirely. Top and htop both show this instant, refreshed every couple of seconds. Useful, but a number which keeps changing still only ever describes right now. Top plots that same information over time, which changes what you can see. Processor use is drawn across the last minute, memory climbs steadily, and the network is flat. Compare that to what top would tell you. A number describes this second and nothing more. A line tells you where it's heading, which is nearly always what you needed. That steady climb isn't a value to worry about yet. It's a leak, and it'll matter within the hour. Disk throughput is plotted on that same timeline. A spike you can see coming beats a reading which only describes the second. Use top when the question is where this is heading rather than where it is. Here's the situation every one of these live tools fails at. The server was slow at 20 to 3 this afternoon. A top is fine now. What happened? A top solves it because it has been quietly writing all these numbers to disk the whole time. Replay yesterday and 2 o'clock looks entirely normal. Move forward and 20 to 3 is your spike, and critically it recorded which processes were running at that moment as well. By 10 past 3 it had recovered on its own. Top can't answer any of that because top only ever knows about now. These are the only questions you get after an outage, which makes a top the one worth enabling in advance. Install a top today, and the next outage will be one you can actually investigate. Every tool, so far, assumes you already know what to look at. That's a fair assumption after 10 years, and a terrible one on your first week. Glances puts every subsystem on a single screen and colors whichever is in trouble. Processor is fine. Memory is fine. Disk input and output is saturated, and it has gone red. Network is fine. You didn't have to know that the disk was the suspect, because Glances applies the threshold for you, and the red panel finds you rather than the other way around. When you're new, not knowing which tool to open is the actual problem, and this is the honest answer to it. Glances is the one to reach for when you know something is wrong, but not what. Every tool up to this point decided its own layout, and you either liked it or you did not. That's fine until the layout hides the one panel you need. Nmon works the other way around entirely. It starts almost empty and you assemble the view you want by pressing keys. Press C and a processor panel docks into place. Press M and memory joins it. D for disk, N for network. You build exactly the dashboard this problem needs, wasting nothing on panels you're not reading. But the reason it has survived since the 1990s is the other mode. -F writes all of it to a file instead of drawing anything at all, so you can leave it overnight and graph it later in a spreadsheet. Nmon was built for capture rather than watching, which is still unusual. Leave Nmon recording overnight, and you'll have a graph instead of a guess in the morning. The name is misleading, so start here. Kill doesn't destroy anything. Kill sends a signal, and a signal is a message. Run it plainly, and it sends sigterm, which politely asks a process to stop. The process receives that message and gets to decide what to do about it, so typically it flushes what it was writing, closes its files, and exits on its own terms. Now, -9 is different. That's sigkill, and sigkill can't be caught or ignored, because the kernel removes the process without ever delivering the message. Kill never gets the chance to save, so whatever was in memory is gone. Send sigterm first, every single time. If sigterm hasn't worked after 10 seconds, the process is stuck, and only then use -9. Kill needs a process ID, and when 8 copies of the same program are running, hunting down all 8 of those numbers by hand gets old fast. Kill all works by name instead, and that's the whole difference. So node running as 4821 goes, node as 4822 goes, and so does node as 5310, which a colleague started and is 2 hours into. All 3 match the name, so all 3 were signaled, and it never asks you which ones you actually meant. On your own laptop, this is a convenience. On a shared server, it's genuinely dangerous. So p-kill with a user filter is the habit worth building instead. Match on a name, and you match everybody's. On anything shared, find the PIDs and kill those. Naming them takes 10 more seconds and costs nobody an afternoon. You start a long backup, close the laptop, come back, and the job died.
Here's why.
Run something in the background normally, and when you close the terminal or the connection drops, a signal called hangup is sent to every job that terminal started. Your plain background job receives it and stops. The fix is in the name. No hup is short for no hangup, and a job started under it simply ignores that signal, so it carries on running with the terminal long gone. One thing to expect, since there's no screen to print to anymore, its output is written into a file called nohup.out. That file is where people forget to look. Better still, use screen or tmux, which we'll get to, and you keep the output as well. Sleep pauses for a fixed time, and it's the least interesting command here until you look at how it does it. Your script runs down its lines, reaches the sleep, and stops. 5 seconds pass with nothing happening at all, and here's the part worth noticing. The processor sits at 0 throughout because sleep asks the kernel to wake it later, and then genuinely stops running. Sleep is not counting in a loop. Then the next line runs exactly where it left off. And you're not limited to seconds, since it takes minutes, hours, and days as well. Because it truly blocks, a sleep inside a retry loop costs you nothing. Sleep is what makes a retry loop polite instead of a machine hammering a server. 2 jobs, and you want them running at the same time. Start job A, which takes 3 seconds, and job B, which takes 7, and put an ampersand after each to send them into the background. Now here's the bug, and it's subtle because nothing looks broken. The script carries straight on, reaches its end and exits, while job B still has 4 seconds of work left. Your CI run goes green on work which never finished. The fix is one word. Wait holds the script until every background child has completed, so its exit status finally means something. Without it, your script reports success on work that's still running. One word at the end of a script is the difference between a real result and a lie. You try to unmount a disk and it refuses with target is busy, which tells you nothing useful. LSOF, short for list open files, tells you who's responsible. Tail is holding a log file open on that disk. Vim is holding a config. Those 2 handles are the entire reason the unmount failed. Now the clever part. On Linux, a network socket is a kind of file as well, genuinely, not by analogy. So the same tool with -I shows you engine X holding port 443, which means one command answers both questions. The next time something says address already in use, this is the fastest way to find out what. Ulsof is the tool which turns a useless error message into a process you can aim. A program fails with an error which makes no sense. strace shows you what it's actually doing because every real thing a program does goes through the kernel. Opening a file, reading a socket, all of it. So open this file is a request you can watch, and the kernel answers no such file or directory. Meanwhile, the program prints something about a database connection, which is why you were confused. The catch is that thousands of these scroll past. So add -e to filter down to just the calls you care about, and there it is, a config path that doesn't exist. strace failed on a missing file, not on the thing it told you. Strace is a big hammer, so reach for it when the error message has already lied to you.
Quick 1.
A process is ignoring your kill entirely. Which signal can't be ignored? Have a think, and pause here if you need longer. Ready? Sig kill, because the kernel delivers it. Drawer 4 is control. PS and PS tree list them. Top shows them moving. Kill signals them politely. LSOF and strace find the cause, so nothing stays mysterious. Drawer 5. Watching the machine properly, so you're not guessing. Load average is the most consistently misread number in all of Linux, and it appears in almost every tool here, so let's fix it properly now. Uptime gives you 3 numbers rather than 1, and the 3 are the point. The first is the last minute, the second is the last 5 minutes, and the third is the last 15. Read them together as a direction of travel. Now the part people get wrong. A load of 4 sounds alarming until you ask how many cores this machine has. On 8 cores, that's half busy, for slots working, for sitting free. On 2 cores, the very same figure means badly overloaded, with work queuing up behind. Always divide by your core count because the number on its own tells you nothing. Load is a queue length, not a percentage, and that one sentence fixes most of the confusion. The first time you run this particular command on a perfectly healthy server, you'll be completely convinced the machine is about to fall over. Free reports 200 megabytes free on a server with 32 gigabytes. That looks alarming, and it's completely fine.
Here's why.
Used is your program's genuinely occupied. Cache is memory Linux borrowed to keep recently read files close by, and it'll hand every byte of it back the moment something needs it. Free is memory doing nothing whatsoever, which is memory being wasted. And available is the figure you actually wanted, what a new program could have right now. Ask for memory, and the cache simply shrinks. Read available and ignore free. Free memory on a Linux box is wasted memory, and the kernel is doing you a favor. You want to know whether this machine is genuinely short of memory, and you want to watch it change rather than take a single reading. That tool is vmstat. There's one trap to know about first. The very first row is an average since the machine booted, so ignore it completely. It's history, not a reading. The second row is the first real one, and one follows every second. The columns to watch are SI and SO, swap in and swap out, which count memory being pushed to disk and pulled back. 0, there's healthy. Anything above 0 means the machine is genuinely short of memory. That's pressure, not just usage, and it's the difference between slow and about to fall over. Watch the swap columns for 10 seconds, and you'll know whether memory is the real problem. The processor is sitting almost idle, and yet the whole machine feels like it's wading through treacle. 9 times out of 10, that's the disk, and I/O stat is how you confirm it. I/O stat reports per device, so you get reads in megabytes a second and writes, which are heavy here but expected for a database. On throughput alone, this disk looks perfectly healthy, and that's exactly the trap. The column which matters is await, which measures how long each request sat waiting before the disk even started on it. A long queue is what slowness actually feels like from inside a program. So when await climbs while throughput stays modest, the disk is your bottleneck. Low throughput with high await means saturated, not idle. When the CPU looks idle and everything feels slow, await is the number to go and read. I/O stat told you the disk is saturated, which is useful and immediately raises the obvious next question. Saturated by what, exactly? I/O top answers that because knowing a disk is busy without knowing who made it busy leaves you nowhere. Here Postgres is writing 88 megabytes a second, which is your answer. rsync is doing 12, which is the backup you scheduled and expected. Everything else is doing essentially nothing. The -O flag shows only processes actually doing input and output, rather than filling the screen with idle ones. Now you have a process ID and a decision. Every monitoring tool tells you something is wrong. This one tells you who. IAstat and IATOP are a pair. One finds the problem, the other names who caused it. The problem with running 4 monitoring tools in 4 separate windows is that none of them agree on when now actually is. dstat fixes that by putting several subsystems on one line, processor split into user and system time, disk reads and writes, and network sent and received. Crucially, they're all sampled at the same instant on the same tick, which means when you see a disk spike in this column and a processor wait sitting in the very same column, you're looking at genuine correlation rather than 2 readings you're trying to line up by eye. One-time access for everything is how you stop guessing at cause and effect. Stat is what you leave running while you reproduce something, because the columns line up. SAR is the tool that absolutely everybody forgets about, and it's also the one which will save you on the day it genuinely counts. SAR, which is the System Activity Reporter, writes these numbers to disk every 10 minutes of every day, whether anyone is watching or not. So after an outage, you can pick a day, even one from weeks ago, and simply read what happened. 2 o'clock was normal. 20 to 3 is your spike. By 10 past 3, it had recovered. But here's the catch which catches everyone. Look at the days before you switched it on and they're empty, because you can't record the past retrospectively. Enable sysstat before you need it, because the outage always arrives before the monitoring does. Turn sysstat on across your machines this week, and thank yourself during the next incident. Sometimes the tool you need doesn't exist, and watch is how you build it in about 4 seconds. Watch takes any command at all, and runs it exactly as you typed it, shows you the output, then waits and runs it again. That's the whole idea. And it matters because a single reading of anything tells you almost nothing. Add -D and it'll highlight whatever changed since the previous run. So when a number creeps upward run after run, the leak becomes obvious without you installing anything. Watch turns any command into a live dashboard, which is why you rarely need a purpose-built tool for a one-off question. Anytime you find yourself pressing up and return repeatedly, watch is the command you wanted.
Quick 1.
Load reads 4 on 8 cores. Problem or fine? Have a think and pause here if you need longer. Ready? Fine, because load counts against cores. Drawer 5 is your eyes on the machine. Uptime and free give the headline. VM stat and IO stat give the detail. SAR remembers yesterday. Watch makes anything live, so you're never guessing. Drawer 6. Disks, file systems, and the one command that deserves fear. DF is short for disk-free, and -H shows you how full each file system is. 62%, so there's plenty of room, which makes it very strange which writes are failing. Here's what's happening. Every single file on the disk needs an inode, a small record holding its permissions, owner, and location. The number of inodes is fixed when the file system is created, and it never grows. So run df-I, and inodes are at 100%. Millions of tiny files, a session cache perhaps, consumed one inode each. The disk is full of names rather than of data. You've free space and nowhere to put anything. So when writes fail on a disk with space left, df-I is the second thing you run. df told you the disk is full. du, short for disk usage, tells you what filled it because du measures by directory rather than by file system. So at the top level varlog is by far the biggest. Home is 26 gigabytes. User is 18. That's the difference between the two commands in one line. Now, don't guess from here. Run it again one level deeper, pointed at varlog itself, and varlog nginx is the actual culprit, holding 41 gigabytes of access logs nobody rotated. Walk down one level at a time, and the answer falls out. df says it's full. Du says what filled it. df then do is the sequence, and it narrows the answer every step. Du works, but in practice you end up typing the same command 3 times over, with a longer path on each attempt. ncdu does that same walk, and lets you move around inside the result. ncdu sorts as it scans, biggest first. Press enter on varlog, and it descends into it. Press enter again on nginx, and there's access logged at 41 gigabytes in a single file. That took 3 keystrokes, where du needed 3 separate commands, and you retyping the path each time. ncdu used the same walk underneath, but you can browse it, which is exactly why it's the one people actually end up installing. Install ngdu on every server. The first time a disk fills up, it pays for itself. fdisk-l reads the partition table and prints it, so you can see that this disk carries SDA1, the boot partition SDA2, the root file system, and SDA3, which is swap. With -L it only looks, it changes nothing at all. That makes it completely safe to run on anything. Now run it without -L, and you're in the editor proper, and this is the part which makes it approachable. Every change you make happens to a copy held in memory, not to the disk. Add partitions, delete them, change types. Nothing is real until you press W to write. And if you've made a mess, press Q, and absolutely nothing happened. Which is why fdisk is safer to explore than its reputation suggests. Because nothing is written until W. fdisk-L is safe to run anywhere, anytime. You plug in a 4 terabyte disk, and fdisk gets awkward about it.
Here's why.
MBR, the old partition table format, uses 32 bits to address blocks on the disk. That sounds like a lot, and with 512-byte blocks it runs out at 2 terabytes. Not a policy, not a bug. The field is simply not wide enough to describe a larger disk. GPT is the replacement, and it uses 64 bits instead, which is a difference so large it stops being worth discussing. So your 4 terabyte disk needs GPT, and parted is the tool which writes one, since fdisk was built for the older format. Over 2 terabytes, MBR physically cannot. Use parted for anything modern, and treat MBR as something you only meet on old disks. Here's a failure that ruins somebody's morning roughly once a year, and it's entirely avoidable once you know that this one small command exists. blkid prints every block device with its file system type and its UUID. Today this partition is /dev/sdb1. The trouble is that a name like that describes a position, not an identity. Plug a USB stick in and reboot, and the names shuffle. What was SDB is now SDC. Anything in stab pointing at the old name now points at the wrong disk. But the UUID never changes because it's written into the file system itself. So put UUIDs in fstab, never device names. Anything you want mounted at boot goes in fstab by UUID, and it will still be there next year. A partition is just a region of a disk. On its own, it can't hold files at all. Something has to write the structure which turns it into a file system, and that something is make fs. Before you run it, the partition holds your data. As it runs, it writes structure. In node tables, superblocks, the bookkeeping of file system needs to exist. Note what it doesn't do. Make fs doesn't erase your files. Make fs simply stops referring to them, which is why the old blocks become unreachable rather than destroyed, and why recovery tools sometimes work. What you're left with is an empty file system, ready to mount. And like most of this drawer, there's no confirmation prompt whatsoever. So read the device name twice before you press return. Read the device name out loud. Check it against LSBLK, and only then press return. FSCK, short for file system check, looks for damage and repairs it. Run it on a live disk, and it warns you that the device is mounted. That warning isn't boilerplate, and people ignore it constantly. The reason it matters is this. The kernel is still writing to that file system while FSCK is reading it. So FSCK makes decisions from a picture that's already out of date and repairs things which were never broken. That corrupts the disk you were trying to fix. So unmount it first, always. Then it sweeps the inode table and the block map properly, and an orphaned inode gets reattached into lost plus found. Never run it on something mounted. Unmount, then check, then mount again. In that order. FSCK is a repair rather than a risk. Windows gives every disk its own letter. Linux does something quite different. There's only ever one tree, and other disks are attached into it wherever you like.
Mount is how.
You pick a folder, here mntdata, which is just an ordinary directory. The new disk is grafted onto that point, and its contents now appear there as though they always had. Now, the part that confuses people. If that folder already had files in it, they're hidden underneath the mount. Hidden, not deleted, and completely untouched. Unmount the disk, and they reappear exactly as they were. One tree, not one per disk, which is why Linux has no drive letters to remember. Mount an empty directory, always, and you'll never wonder where your files went. Unmount refuses with target is busy, which sounds like an obstruction and is actually doing you a favor. Unmount only ever happens because something still holds a file open on that disk. So LSOF names the culprit. Tail is holding a log file open on that disk, and until that process lets go, nothing else is going to happen here. Kill it and the handle closes so the unmount works first time. What you shouldn't do is reach straight for -F to force it, because there may be writes sitting in memory that haven't reached the disk yet, and forcing throws them away. If you genuinely can't stop the process, -L is the gentler option. It detaches the file system and finishes the job once the last handle closes. The refusal is protecting data. When a disk won't unmount, lsoff answers it in one command, so reach for that instead of force. Lsoff first, kill second, unmount third. That order never loses a write. And here's the answer to the question I open with. DD copies blocks and asks nothing of anybody. Two arguments do all the work. IF equals is the input, the thing you read from, and OF equals is the output, the thing you write over. Used properly, it's excellent. Read your disk, write a file, and that's a genuine full backup. Read the file back onto a spare disk and you've restored it. Now swap one letter so the output is /dev/SDA, and that's your running system being overwritten while you watch. No prompt, no progress bar, no undo. For characters, add status equals progress, so it at least tells you what it's doing. Read the of equals argument twice, out loud, before you press return. Every single time.
Quick one.
DF says space is free, but writes fail. What ran out? Have a think and pause here if you need longer.
Ready?
In nodes, every file consumes one. Drawer 6 is the disk. DF and D you find the space. Mount and BLK ID attach it. F disk and make FS prepare it. DD destroys it if you mistype, so slow down here. Halfway. If this is landing, subscribing genuinely helps, and there's a lot more of it below. Drawer 7. The network, starting from this machine because that's where you debug. Networking on a single machine is really 3 questions stacked on top of each other, and IP answers all 3 of them. At the bottom, the link layer is the interfaces themselves. Is there a cable in, and is the device up? Above that, IP address shows the addresses bound to those interfaces, so 10.0.0.5 is what this machine answers to. And above that again, IP route decides where a packet goes when it leaves, which is why you see a default route saying anything not on this network goes to the gateway. 3 layers, 1 tool. IP replaced ifconfig because ifconfig couldn't describe modern routing or multiple addresses on one interface. Learn IP address, IP route, and IP link, and you can describe any machine's networking. When something won't connect, this is the first thing anyone reaches for, and most people only ever read half of what it tells them. The command is ping, and what it does is simple. A packet leaves your machine, crosses the gateway, and the far end replies, here in 12 milliseconds. Do it 4 times and you learn 2 separate things. The first is how far away it is. The second is more important. Watch packet 3. It leaves and never comes back. That's loss, which is a completely different problem from slowness. 1 packet in 4 missing will make a connection feel broken, even though the average time still looks perfectly healthy. So read the loss figure first, because the average hides it. Run ping with -C4, read the loss line first and the latency second. Ping tells you whether the far end is reachable, but when it's not, it says nothing about where along the way things went wrong. Trace route tells you the whole path, and the trick behind it's genuinely clever. Trace route sends a packet allowed to travel exactly 1 hop, which expires immediately, and the router that killed it politely reports back. That gives you hop 1, your own router. Then it allows 2 hops, then 3, walking outward 1 at a time. So hop 4 is your internet provider, hop 7 answers with nothing whatsoever, and hop 9 is the destination. Now, about hop 7. Those stars aren't automatically a fault, because plenty of routers are configured never to reply, and your traffic passes straight through them regardless. Traceroute tells you where the path goes. It takes judgment to say where it breaks. Traceroute has a real weakness. It runs once, and then stops. If your problem is intermittent, a single pass will very often miss it entirely. MTR is traceroute and ping combined, so it keeps probing every hop hundreds of times and builds up statistics. Now the picture is much clearer. Hop 4 is dropping nothing. Hop 7 is dropping 38% of packets. But look at hop 9, which is clean again, and that's the actual clue. If loss at 1 hop clears at the next, that router is almost certainly just rate limiting its own replies rather than dropping your traffic. 1 run can lie. 100 runs cannot. Leave MTR running for a minute before you phone anybody about a network problem. Almost every sysadmin alive has this exact flag block committed to memory without ever having sat down and decoded it. So, let's decode it once. Netstat with -TULPN, -T is TCP, -U adds UDP, -L narrows it to listening sockets, and -P shows which process owns each. The output is exactly what you want. The problem is how it gets it. Netstat reads through the proc file system, 1 file per connection, and on a server with thousands of connections, that's thousands of reads. SS asks the kernel directly, once, and prints output which matches flag for flag. The muscle memory still works, but SS is the one that finishes on a loaded machine. Learn the SS flags now because Netstat isn't installed by default on newer systems. SS is short for socket statistics, and SS shows you what this machine is currently prepared to talk to and to whom. Port 443 is Nginx listening. Port 22 is SSH listening. Listening means the service is genuinely up and accepting connections. That's what you check first when a service won't answer. Now filter by state instead, and the listeners drop away, leaving an established connection, which is a conversation actually in progress with a real peer at the other end. Here's the diagnostic that saves you an afternoon. If SS says a service is listening and yet nothing can reach it, the problem isn't the application. It's a firewall, a security group, or the address it bound to. Stop debugging the app. SS-TULPN is worth memorizing because listening and reachable are 2 different claims and only one is the application's job. And MCLI manages networking from the command line, and there's one distinction that trips absolutely everybody the first time. F0 is a device, the physical port on the machine. Wired 1 is a profile, which is a saved bundle of settings, an address, DNS servers, and routes. Wired backup is a second profile for that very same device. So a device is hardware and it doesn't change, while a profile is configuration and you can keep as many as you like. When you bring a profile up, it snaps onto the device, and switching between them changes the machine's entire network identity without you touching a cable. One device, many profiles. Think of it as a device and a set of profiles, and nuclei stops being confusing. The link is completely saturated. Everything on the box feels slow, and you'd very much like to know what exactly is filling it up. If top gives you the first half of that answer because it groups traffic by pair, this machine and whoever is on the other end. So 38 megabits is going to 10.0.0.9, which is dominating the link. DNS is essentially nothing. Monitoring is essentially nothing. Now that's genuinely useful, because you now know where the traffic is heading. But notice what's missing. There's no process name anywhere on this screen, so you still can't say which program is responsible. That's the next tool. If top answers where and never who. If top and nethogs together answer the whole question, so install both while you're there. If top told you where the traffic was heading and then stopped just short of the genuinely useful part, which is what to do about it. Nethogs tells you what's sending it because it groups by process rather than by address. And the answer is immediate. Rsync process 4821 is eating the link. Nginx is serving normally. SSHD is your own session. Now you've a process ID, which means you've something you can actually act on. Renice it, throttle it, or wait for it. If top answered where, nethogs answers who. And who's nearly always the question you walked in with, because you can't stop a destination, but you can certainly stop a process. Nethogs is the one that ends the argument about whose job is saturating the link. Sometimes the only question you actually have is this one, and honestly nothing more than this. Is the pipe full, yes or no? Nload strips everything else away and hands you two numbers. Incoming, 41 megabits a second. Outgoing, 88. No addresses, no tables, nothing to interpret. Just the shape of the traffic over the last minute. And that's enough to answer the question, because if this link is 100 megabit, then outgoing is very nearly maxed out, and you've found your ceiling. When you already know what you're asking, every extra column is one more thing standing between you and the answer, which is why a deliberately small tool earns its place. When you already know the question, a small tool beats a dashboard every time. Quick 1. Your service is listening on 443, unreachable outside. Look where? Have a think, and pause here if you need longer. Ready? The firewall, because the service already proved it's up. Drawer 7 is the wire. IP says who you are. Ping and trace routes say what you reach. SS says what's open. The bandwidth tools say who's loud. Drawer 8. Reaching other machines, which is most of the job which matters. DNS turns a name into an address, and when it goes wrong you need to see the whole exchange. DIG is short for Domain Information Groper. You ask a resolver, here 1.1.1.1, and it answers. What comes back is an A record, which maps the name to an address. Alongside it sits a TTL of 300, meaning cache this answer for 5 minutes, which is exactly why a DNS change doesn't appear everywhere at once. If you only want the value, plus short strips all of it away. But the full output is the point. It tells you who answered and how long that answer stays true, which is why DIG is the one to reach for. DIG is the tool to reach for the moment you suspect DNS, which is more often than you'd think. DIG is thorough, and at 2:30 in the morning, thorough is sometimes considerably more than you actually want from a command. Host answers that same question in one readable sentence. Put all three side by side, and the choice is obvious. DIG gives you the full record with its TTL and which server was authoritative. DIG plus short gives you nothing but the bare value, which is what you want inside script. Host sits in the middle in plain English. Host's the right tool for a sanity check. Does this name resolve, and roughly where? And the moment the answer surprises you, you switch to DIG. Use the smallest tool which answers the question. Host for a quick yes or no. DIG the moment that answer surprises you. This next one is older than DIG and host, and it misleads people every single day because of 2 words in its output. The command is nslookup. Nslookup prints the server you asked, then the phrase non-authoritative answer. Almost everybody reads that as a warning that something has gone wrong. Nslookup means nothing of the sort. Nslookup means this answer came out of a cache. The authoritative server is the one which actually owns the domain and holds the original record. Your resolver asked it at some point earlier, kept the answer for the length of its TTL, and handed you the copy. That's DNS S working exactly as designed. Non-authoritative is the normal case, not a fault. So if somebody sends you that output as evidence of a fault, it usually isn't one because a cached answer is the normal case. This last one isn't really about your own machine at all, and it's very easy to skip straight past, but it'll save you an entire afternoon eventually. Who's asked the registry who owns a domain? You get the registrar it was bought through, the expiry date, which here's 28 days away, and the name servers that answer for it. That expiry date is the line which matters, because an expired domain doesn't fail gently. Everything stops at once. Mail stops, because the MX records go with it. And here's the cruel part. Your certificate can still be valid for another year, so nothing warns you. Monitoring that checks the site is up won't catch it either. So put that date in your own calendar. The renewal email lands in a mailbox nobody reads. Check expiry first. Put every domain you own in a calendar, because nobody reads the registrar's email. A domain quietly expiring will cost you a morning you could have spent on anything else. SSH keygen makes a key pair, and the two halves aren't interchangeable. The private half, with no extension, never leaves your laptop under any circumstances. The public half, ending pub, is the one designed to travel. That's its entire purpose. So SSH copy ID takes that public half and appends it to a file called authorized keys on the server. After that, logging in needs no password because the server sends a challenge only something holding the private half can answer. The .pub suffix is the one that travels. Send the other, and you've handed somebody your identity, which no password change will undo. You've keys working, and now you actually need to get a build artifact from your own laptop onto that server without messing about. The tool is SCP, short for Secure Copy, and there's nothing new to set up. Your local file rides the channel SSH already built, using the same keys, and lands at the remote path. Now, the detail which catches people. That colon is doing all of the work. SCP is the one character telling SCP that what follows is on another machine. Leave it out and the command still succeeds, except it was a local copy and you now have a file called prod sitting next to the original. No error, no warning. Just a deployment which never happened. Check the colon, then check the destination path, and SCP will do exactly what you meant. SCP sends everything every time. rsync is cleverer because it compares the two sides before it sends anything at all. Here 14,000 files are identical and get skipped, 3 have changed so those go, and 1 is new so that goes too. The result is 2 megabytes on the wire instead of 4 gigabytes, which turns a 20-minute transfer into a 2-second one. 2 habits worth building. --dry run shows you exactly what it'd do and changes nothing, and the trailing slash matters enormously. Source slash copies the contents. Source, without copies the folder itself. Dry run it first, every time. Dry run. Read the plan, then run it properly. That habit will save you a restore. Before you debug an application, it's worth proving you can even reach it. NC, short for netcat, hands you a raw socket with no protocol in the way, which answers exactly that. 5432 answers, so Postgres is open and listening there, and that rules out one whole class of problem. Now try 6379 instead, and it's refused straight away. That refusal is good news, because refused means you reached the machine, and it told you nothing is listening. Compare that with nothing at all, just silence until it times out. That's a firewall dropping your packet without a word. Refused and timeout mean opposite things. One is an application problem, the other is a network problem. One NC command tells you whether to debug the application or the network, which saves an hour. wget is short for webget, and it's built around one assumption. You want this file, and you want it even if the network is unreliable. So take a 4 gigabyte download on a shaky connection. wget drops at 61%, which is infuriating. But the partial file is still sitting on your disk, so add -c for continue, and it resumes from 61% rather than starting again. wget goes further than that. -r follows links and will mirror an entire site, and it retries on its own without you sitting there watching. wget is for downloading things. curl, which is next, is for talking to them, and that distinction is worth keeping. Where wget fetches a file and finishes, curl holds a conversation with the server. Start with curl and a plain get, the default. For a quick health check, that's genuinely all you need, and it's all most people ever use it for. The real value comes when you need to send something rather than just fetch it, and which means controlling 3 parts yourself. Method, headers, and body. Build it up piece by piece. -x sets the method. Post, not get.
-tldr.
-d carries the body. Send it and 201 created comes back. Add -i for the response headers, which is often where the clue hides. You're assembling it by hand, with no library to misreport the answer. Curl's the fastest way to see what a server really said. Curl is worth learning properly because it's how you find out what a server truly returned. Quick 1. Resyncing a huge folder. Barely anything changed. Which tool? Have a think and pause here if you need longer. Ready? rsync, because it sends only differences. Drawer 8 is everything past this box. Dig resolves names. SSH gets a shell. SCP and rsync move files. NC and curl test the far end. Drawer 9. Archives, scheduled jobs, and sessions that survive because you won't. tar is the most Googled command on this entire list, and honestly, that's avoidable. The name is short for tape archive, from back when, which was literal. Those 4 letters after the dash are 4 separate instructions wearing one code, so let's take them apart. C creates a new archive, gathering many files into one. Z compresses that archive using gzip. V is verbose, printing each name as it goes in. And F names the output file, which is why F always comes last. Whatever follows, it's the file name. Now the part that saves you. Swap the C for an X, and the whole thing runs backwards and extracts, while the other 3 letters stay exactly as they were. X to extract, C to create. tar-xzvf to extract, tar-czvf to create, and you're done with tar. Gzip, which is short for GNU-zip, shrinks a single file, and it's very good at it. 41 megabytes of log goes in, and 6 megabytes comes out. But there's a behavior here which catches everybody exactly once. The original file is gone. Gzip didn't make a copy alongside it. It replaced it, and you now have only the compressed version. That surprises people every single time, particularly inside a script that expected to read the original afterwards. So add -k for keep, and both files survive. And it's quick. That took about a second. Gzip replaces by default, so learn -k before you need it rather than after. Use -k whenever a script downstream still expects the original file to be there. Gzip is fast, and for almost anything you compress, it's good enough. Every so often you want the file as small as it'll go. That's when you reach for bzip 2. Run both against the same log. Gzip finishes in a second, giving 6 megabytes. bzip 2 takes 8.5, giving 4.5. You're paying 7 times the processor time for a megabyte and a half. Whether that's worth it depends on what happens next. For a log you rotate nightly, it's a waste. For an archive you keep for 7 years, it's obviously right. Write once, read almost never, is where it pays. XC goes further still. But gzip stays the default because it's fast enough and always installed. Match the compressor to how often you pay the cost back. Gzip for anything you touch often, bzip 2, or XC for anything you're storing and forgetting. You've an archive which needs to go to somebody who has quite honestly never opened a terminal window in their entire life. Zip is what they can open, and the difference from tar.gz is structural. A tar.gz is a single compressed stream, so to reach one file in the middle you have to decompress everything before it. Zip compresses each file separately and keeps an index at the end of the archive. That means you can pull one file straight out without touching the rest. And it opens with a double click on any operating system. So the rule is really about who opens it. Send zip to people and tar.gz to servers. Scheduling on Linux comes down to one line of 5 numbers, and almost everybody copies that line from somewhere else without ever reading it properly. Cron is 5 fields in a fixed order, and that order is the whole trick. The first field is the minute, 0 to 59. The second is the hour, 0 to 23. The third is the day of the month. The fourth is the month. The fifth is the day of the week, where 0 is Sunday. Then a star simply means every one of whatever that field counts. So this line means 2:30 in the morning, on Mondays only. 5 stars means every single minute of every day, which is how people take servers down by accident. Read the 5 fields left to right, and any cron line becomes plain English. A cron is the schedule. Cron tab is how you edit it. -e opens your table in an editor, and the important bit is that it validates the file when you save. A syntax error is rejected there and then, with a message telling you, Now compare that with editing the cron tab file directly on disk, which people do all the time. That skips the check completely, and cron will simply skip the broken job silently forever. No email, no log entry, nothing. Which is why -L matters. It prints what's actually loaded right now, and that's the only real proof your job exists. A schedule you never verified isn't a schedule. Always use cron tab-E, then cron tab-L to confirm what actually got installed. A script is just a file with commands in it, and yet the first time you run one you get permission denied. Here's why. New files aren't created executable, which would be a terrible default. So change mod plus X flips exactly that one bit, and the very same command now works. 2 more details. The first line of the script names the interpreter that should run it, and that line is called the shebang. And you have to write / in front of the name because the current folder is deliberately not in your search path. That's a security decision. If it were, dropping a file called ls into a shared directory would hijack everyone's commands. Shebang, chmod plus X, then /. 3 things, and your script runs anywhere. Alias binds a long command to a short name, and the trap is about where that binding lives. Type it at the prompt and it works straight away, but only inside this one shell, and only until you close it. Open a new terminal, and it is gone. If you want it to outlive the session, append it to your rsync, which every new shell reads on startup, and now it survives forever. But here's the one which catches people. A script still can't see your aliases, because a script runs a non-interactive shell and rsync isn't read at all. Which is exactly why a command that works perfectly when you type it fails the moment cron runs the same line. Put your aliases in rsync and put the real command in your scripts. env shows the variables a command inherits when it starts. Path tells the shell where to look for commands. Home is your home directory. And every process you start inherits a copy of this whole set, which is how configuration reaches a program without a config file. Now the genuinely useful trick here. Put debug equals 1 in front of a command, and you've set that variable for that process alone, and for anything it starts. The very next command you type has no debug at all. Nothing else on the machine ever saw it. That matters on a shared box, because exporting a secret into your shell leaves it sitting in the environment of everything you run afterwards. Setting a variable in front of a command is the safest way to try something once. History keeps everything you've typed, numbered, and there are 3 ways to reach back into it. Bang followed by a number runs that exact line again. Bang bang runs the previous command. And the one you'll genuinely use every day is this. You run something, it fails because it needed privilege, and rather than retype any of it you just run sudo bang bang. Better still, Control-R searches backwards through your history as you type. One warning though. All of this is written to a file in your home directory, so any password you ever typed as part of a command is sitting on disk in plain text. Which is a good reason never to put one on a command line. Sudo bang bang will save you more typing this year than any other 2 words here. Start a long job over SSH and it dies when the connection drops, because your session belongs to that connection, and when it closes, everything inside goes with it. Screen fixes that properly. -S creates a session which lives on the server itself, and the job runs inside that session rather than inside your connection. So now your connection can drop, your laptop can sleep, and the work carries straight on. When you come back, screen-R reattaches you, and everything is exactly where you left it. And Control-A then detaches deliberately. The session belongs to the server, not to you, which is the whole point. Start anything long inside screen or tmux, and a dropped connection stops mattering. tmux does everything screen does, so you get the same survival across a dropped connection, and then tmux splits the terminal into panes. That sounds cosmetic until you use it. One pane holds your editor. Another holds the logs, live as you work. tmux is one session holding both, so you're watching your change and its effect at the same time without switching windows. Attach by name from any machine, and the whole layout comes back. One practical note. Control-B is the prefix key for everything in tmux, where screen uses Control-A. The muscle memory doesn't transfer between them, so pick one and commit to it. tmux is worth an afternoon of practice, because it changes how you work on servers. Here's the distinction which catches people out, and getting the 2 confused costs them an outage. A service has 2 separate switches, not one. Here it stopped. Start it and it's running right now, serving traffic, completely fine. But it'll not come back after reboot, because that's the other switch. Enable is the one that makes it start at boot, and it doesn't start it now. So reboot this machine, and only the service you enabled comes back on its own. Status shows you both states at once, which is why it's the command to run when something isn't behaving. You almost always want both, and enable dash dash now does the pair in one go. System tool enable dash dash now is the command you actually wanted nearly every time. The mistake with journalctl is treating it like a file and scrolling. Journalctl is a database, and you query it. -u narrows to one service, which is usually the first thing you want. Add -b and you only see this boot, so yesterday's noise disappears. Add -p error, and you only see errors and worse. 3 filters, and what's left is the thing you were looking for. And when you want to watch it happen, -f follows the journal live, exactly like tail-f on a log file. The habit worth building is composing filters rather than scrolling, because every flag narrows the set and they stack. Compose the filters and journal tool goes from overwhelming to the fastest log tool you own. When a piece of hardware starts to fail, the kernel notices it long before anything gets written down in a log file anywhere. The command is dmesc, and dmesc prints that buffer, which isn't a log file at all. Dmesc's fixed in size, and it's a ring, which means new messages come in one end, and the oldest are pushed off the other and lost. -t makes timestamps readable. By default, they're seconds since boot. Now why you care? A disk starting to fail, a cable going bad, memory throwing errors. All of it appears here first, long before anything writes it to a log file. So check it early. On a busy machine, that buffer wraps, and the message that explained everything is simply gone. Dmesc-t piped into tail is worth running whenever a machine behaves strangely. Quick 1. You started a service and a reboot killed it. What was missed? Have a think and pause here if you need longer. Ready? Enable, not just start. Drawer 9 runs without you. tar and gzip package it. Cron schedules it. Systems-ctl and journals-ctl supervise it. tmux keeps it alive while you sleep. Drawer 10. What to do when you're stuck, which is why these exist. The manual isn't one book, it's numbered sections, and knowing that changes how useful it is. Section 1 is user commands. Section 5 is file formats. Section 8 is administration. The same word can appear on several of those shelves. So man password gives you the command that changes a password. But man5 password gives you the format of the etc. password file, a completely different page answering a completely different question. The number in brackets at the top of any page tells you which one you're reading. If a manual page seems to be answering the wrong question, you're almost certainly on the wrong shelf. When a manual page seems to answer the wrong question, check the section number first. Here's the situation the manual normally fails at. You know exactly what you want to do, but you don't know what the command is called, and man needs a name you don't have. Apropos solves it, because it searches the one-line descriptions of every manual page rather than their names. So ask it about disk usage and backcomdu, which estimates file space usage, df, which reports file system space, and ncdu, the interactive one. 3 tools from 3 different sections found by describing the job. Man-k is the identical command with a shorter name. Apropos answers the question you actually have, which is usually what was that thing called. Apropos is the command to remember for the days you've forgotten every other one. The manual is complete, and completeness isn't always what you need at 4 in the afternoon. The page for tar runs to 1,241 lines. TLDR is thorough and entirely correct. TLDR, which stands for too long, didn't read, gives you 8 lines instead. The handful of things people actually do with the command, written as examples you can copy. And what you wanted was almost certainly one of them. These aren't competitors. The manual is the reference you go to when the detail genuinely matters and you need to be sure. TLDR is the reminder you want when you've done this before and simply can't recall the flag order. Keep both. Install TLDR today. TLDR'll save you the 1,200 lines you didn't want to read. The manual settles arguments. TLDR just gets you back to work. There are 3 kinds of documentation, and this is the third. The manual is written by the people who wrote the tool. TLDR is written by the community. Cheat is written by you. -e opens your own sheet for a command, and whatever flag you keep forgetting gets written down once, then recalled later exactly as you left it. That matters more than it sounds, because your notes can hold the details no general documentation ever will. Your server names, your paths, the exact rsync incantation your deployment needs. Write it down the second time you look something up because there's always a third time, and you'll not remember then either. Your own notes, written once, beat rereading somebody else's documentation 3 times. A graphics card is installed, the machine boots perfectly well, and yet absolutely nothing on the system appears to be using the thing at all. LSPCI-K is where you find out why, because LSPCI lists hardware on the bus with the driver bound to each piece. The device is present, so the bus can see it. A kernel driver is in use, here I915. Both of those need to be true. When that driver line is missing entirely, the hardware is present and completely unusable, and nothing will tell you. No error, no warning, it simply isn't used. That's a missing driver, not broken hardware, which is where an evening disappears. Present isn't working. Present and working are 2 different states, and LSPCI-K is what tells them apart. Check the driver line before blaming the card, because that's where the evening goes. Everything you plug in over USB forms a physical tree, whether or not you ever picture it that way, and that shape explains a problem that otherwise makes no sense. LSUSB-T draws the tree. At the top sits bus 1, the root hub on the motherboard. Into one port you've plugged an external hub, and hanging off it are a keyboard and an external drive. Here's what which tells you. Those 2 share one link back to the machine. The keyboard needs almost none of it, the drive would use all of it. So when that drive runs slowly and nothing about the drive changed, the answer is in this tree. Move it to a port on the machine which has a link of its own. Nothing was broken, it was sharing. Before you replace a slow drive, look at the tree and try a different port. USB bandwidth is shared per hub, so where you plug something in genuinely matters. Last one. You know the job, not the command name. What do you reach for? Have a think and pause here if you need longer. Ready? Apropos, because it searches the descriptions. And that's the bench, all 10 drawers filled. 109 tools, and you never have to memorize one, because you only need to know which drawer to open. If one of these saved you a search, subscribing helps. And if you take one thing away, make it this. Check what DD points at twice before you press enter.